Finally, we will end this section 3.1 with the uniqueness of the continuous fraction expansion. Lemma. This is 3.4 in the book. The map that sends the sequence. This is an infinite sequence. A0, A1, which lives in the Cartesian product of the non-negative integers and all infinite sequences of positive integers. A0 is a non-negative integer, and the rest all consists of positive integers. To the limit in 3.10, let me recall what 3.10 means. 3.10 means U, which is this infinite continued expansion, which is the limit of such finite continued fractions as n goes infinity. And this lemma states that the map that sends the sequence to this continued fraction is injective. Now we prove this. The proof is not hard. So first we let this infinite vector A0, A1, A2, be in here as given. Then you know this limit, this infinite continued fraction. We know this converges, and this is clearly positive because A0 is non-negative and those A1, A2 are all positive. And you also know that we have the following inductive relation. That this guy is equal to A0 plus 1 over the infinite continued fraction starting with A1. This holds because this limit exists. Because the only thing you need to do is to take the formula in the finite case and let n go to infinity. And you get this equality for the infinite case. Note that this is U. Okay, so now we have, so this is U. You can easily see from here that U lies between A0 and A0 plus 1 over A1. And this is contained in the interval of unit length from A0 to A0 plus 1. So, what does this tell us? This tells us that U uniquely determines the non-negative integer A0. And using this inductive relation again, we have, so if you manipulate this a little bit, what you get is that 1 over U minus A0, 1 over U minus A0 is equal to a1 plus this thing, which is the infinite fraction, the infinite continued fraction starting from a1. And what does this tell you? Because u uniquely determines this 1 over u minus u a naught. And this number will in turn uniquely determine a1 by the same argument as above, by replacing u with this fraction. So specifically, what I mean is that 1 over u minus a naught, which lives in by the same argument a1, the interval from a1 to a1 plus 1. So u uniquely determines a1. Now you repeat this procedure. Now, by iterating the procedure, we know that all the terms in the continued fraction can be reconstructed from u. And that finished the proof of uniqueness, because our proof shows that if you are given a u, then the pre-image of u under this map is uniquely determined from u. There couldn't be another sequence of integers that gives you the same u. It has to be unique. So this proves the uniqueness. And finally, I want to make a remark here that this procedure gives you a way to find a naught, a1, a2, etc. with a real number u. So you can find those integers a sub n's with the given real number u. But if u is an irrational number, in which case you get an infinite sequence, although you know that that sequence must converge by our previous result, and you know that sequence is constructed from u, but you cannot conclude easily that that sequence necessarily converges to the given real number u, or given irrational number u. You know that sequence is constructed from u, and you know that there's a limit for this continued fraction, but you don't know why this continued fraction is necessarily equal to u. Or you don't know why that limit, I should say, you don't know why that limit of finite continued fractions is necessarily equal to u. We will pursue further about this issue in the next section.